Thanks for joining in into our presentation. My name is Jeronimo Grandi, and today I'll present the design and simulation of next-generation augmented reality user interfaces in virtual reality. This work was done in collaboration with Zekun, Mark Ogren, and Regis Kopper from both University of North Carolina, Greensboro and Duke University. The goal of this paper is to leverage VR as a tool to design and simulate next-generation AR user interfaces. Augmented reality technology, particularly optical see-through HMDs, are still in active research and development. Key parameters such as field of view, tracking, and form factor must be improved before being deployed to real-world production. As such, the adoption of AR technology can still take several years. While developing under current technological constraints is valuable, AR hardware may not be able to support novel designs and account for future capabilities. VR, on the other hand, is well suited for this task. VR can be leveraged to obviate present AR constraints, not only to imagine and passively visualize the likely direction of next-generation AR UIs, but to realistically and precisely interact with these proposed interfaces. The methodology proposed here aims at maximizing user acceptance of the interfaces once the technology becomes available. The methodology has 4 high-level phases: requirement analysis, prototyping, implementation in VR, and evaluation. The goal of the requirement analysis is to gain insight into the needs of our users. This phase involves performing field research in which we closely observe and learn about existing user processes and practices. In this way, we can identify opportunities and gaps where next-generation UIs stand to produce greatest benefits. By gaining a better understanding of what the user needs, we can contribute to AR solutions that supplement rather than simply replace time-proven processes. For the prototyping phase, we start with the knowledge gained during the requirement analysis. Our prototypes are incrementally developed using an iterative approach, gradually progressing from rough, low-fidelity concepts, sketches, and storyboards to working mock-ups. We obtain feedback from the users early in the process, discuss possible scenarios, and progressively refine our designs. The fidelity is increased with each iteration, leaving the small details for the end. The implementation phase involves transferring the prototypes into a fully functional VR simulation. In this process, we implement a real-world scenario and the standard interactions and integrate the simulation of the AR interfaces. This phase also includes the design of system control mechanisms, such as menu interfaces and custom-made input devices to track specific props in VR. Evaluation of the proposed designs aims at assessing the effectiveness of simulated AR user interfaces. Quantitative feedback and user studies can guarantee the validity of designs and transferability of simulated UIs into the real world. We also might detect opportunities where user experiments would provide answers to specific design elements. For example, a user study could help us to find the best setting for an alert system that we are creating. We demonstrate the potential benefits of designing and prototyping AR UIs in 2 specialized domains in public safety. One is law enforcement, the other one is fire safety. These fields have high-stakes operations that would potentially benefit from next-generation UIs in the future. By following our proposed methodology, we were able to design some features that have the likelihood of positive impact in law enforcement. After group discussions with first responders, we agreed to explore the contributions of next-generation user interfaces in traffic stops. Traffic stops represent one of the most common interactions between police officers and civilians. They are often a low-risk routine, but have the potential of a risk escalation. The standard operations that we are simulating in this traffic stop scenario are: assess vehicle and occupants, verify documents and records, and proceed with required actions. And during the prototyping phase, we created a storyboard where we can showcase the interface features that we want to implement in the traffic stop scenario. And the first feature is the on-demand information display. The on-demand display shows a summary of relevant information about the traffic stop, such as information about the driver and also the vehicle. And the video shows the implementation of the display in VR. As you can see, by using the interface, the police officer can quickly access and receive data while having both hands free to perform other crucial tasks. The Situation Awareness interface is designed to help the officer perceive key elements in the environment and to assess potential risk escalation. Simulated pattern recognition tags key elements such as plates, driver's licenses, and suspicious objects. An alert system provides a status update, and it works in 3 different levels depending on the severity of the situation. And now I'll show a video about the traffic stop being conducted using the interface features that we have proposed. So once they look at the license plate, the system scans it, and then after a while, the user receives an alert informing that the information about the vehicle is ready. In this case, the vehicle is clear. In another time, the vehicle can have other problems such as the registration is expired. After checking the information about the vehicle, the user approaches the driver and starts the interrogation. Eventually, they ask for the driver's license. And once the system scans it, it informs the officer information about the driver. In this case, a red alert can mean that the driver is a potential criminal. For the fire safety, we have created a search and rescue scenario in a burning building. Burning buildings are dynamically changing scenarios and risks can escalate really quickly. Navigation inside a burning building can also be a challenge for firefighters since smoke can block their views. Moreover, heat-tolerant gloves limit their ability to perform fine-grained interactions. By adopting a next-generation augmented reality user interface, environmental perception is enhanced and uncertainties are reduced. For the search and rescue scenario, we are simulating 3 high-level operations. First is to explore the burning building, second is to rescue the victim, and the third one is to avoid hazards. And on top of these simulated operations, we proposed the UI features that can enhance the firefighting operations. The first one is the HUD information, where the firefighter can see the room temperature, air bottle level, and orientation, and also the floor level that they are in. The second is the team identification. The user interface tags the firefighters and shows their location in the environment. We use icons floating over the teammates, and we display their names and also the distance between each firefighter. An indoor guidance system is crucial for firefighters to navigate inside a burning building. Our interface includes 2 key features. One is a dynamically generated minimap, and the other one is a path generation. The indoor guidance minimap automatically updates a functional floor plan as firefighters explore the structure. And the path generation function enables the requests for directions from a remote team leader. The interface also allows for the deployment of markers on the environment. The markers can represent blocked paths, hazards, and also possible exit routes. The markers are always visible and are shared among the firefighters. The alert system sends a color-coded based warning to the peripheral view of the firefighter if they are in danger. For example, in the video, the air bottle level is low, so he receives an alert informing it. And this is the video showing the complete operation being performed. As you can see, he found a possible exit and he's following the other firefighter. He receives an information that the victim was found. So now they request the path for the victim, but there is a debris in front of it. He removes the debris, tags the fire, and assesses the victim. The victim is responsive, so he requests an evacuation route. The evacuation route is sent, and then he proceeds evacuating the building. So the simulation of AR interfaces in VR allows for the design of ideal user experiences unconstrained by current technology limitations. Also, virtual reality has its own limitations, and just as a VR experience, it may not transfer to the real world. And that's why the UIs need to be validated with end users of the application. And the comparison of simulated AR with implementations in real hardware would establish the validity of the interfaces designed. And these evaluations and comparisons are left for future work. Thank you for your attention. We will be happy to take questions over email and in a designated Q&A session.